I'm very honored to be given this wonderful opportunity. Good day, everyone, and I'm pleased to present to you today on the title of The Evolution and Future of AI in Radiology, Pioneering the Future with Abierto. And this session is hosted by Canon Medical Systems Corporation. And I want to mention that English isn't my first language, so I apologize if I don't express myself clearly at times, and I appreciate your understanding and patience. And my name is Tomohiro Kikuchi, and I hold an MPH and PhD degrees, and I currently serve as an assistant professor at the Data Science Center at Jichi Medical University, and until last year, I was a part of the Department of Radiology, and I'm a board-certified diagnostic radiologist. And in terms of education, I completed my MD at Niigata University and PhD at Jichi Medical University, and then Master of Public Health and at the University of Tokyo. And recently, my work has become a diverse mix, combining elements of being a radiologist, medical AI researcher, and data scientist. And preparing this presentation, I have focused primarily on the perspectives of the radiologist, which account for about 18% of the content. The remaining 20% is from the viewpoint of medical AI researcher. This means that today's talk will focus more on the clinical applications and the user experience of AI in radiology, rather than technical development. With that in mind, by attending this talk, I hope engineers will gain insights into how a radiologist like me perceives AI. And for clinicians, I hope this presentation inspires new ideas for your project. And for those who are neither or already familiar with this field, I hope you simply enjoy the content. And here is the agenda for today's presentation. And I will begin with a discussion of the current state of AI in diagnostic radiology, which will take about 20 minutes. And next, we'll move on to the evolution direction of AI in radiology. This will also take about 20 minutes. After that, I'll take a brief explanation about the evolution of radiology itself. And finally, I conclude the presentation with a 1-minute summary, trying everything together and leaving you with key takeaways from today's talk. So it's gonna to be a bit a long presentation, so please feel free to relax and listening comfortably. And I should mention though, I've never spoken in English for 15 minutes straight, so I'm a little nervous about it. And let's start first section. Then let me start by giving you my conclusion up front for this session. AI has shown that it can be clinically useful, especially when tasks are broken down into individual components, like individual tasks like detecting brain aneurysms on MRI or lung nodules on CT. But even with all this potential, the number of AI solutions actually in use in clinical practice is still pretty limited. That said, I really believe we are about to see a big shift with more AI solutions being adopted thanks to the rise of foundation models and multimodal large language models. In the following slides, I will explain how I hold these views. And in the field of image recognition AI, there are 3 classical tasks, that is, classification and segmentation and detection. The classification involves categorizing the entire image into a specific class. Segmentation assigns a class to each pixel, helping to delineate object and their boundaries. Detection focused on identification and localization specific objects within an image. In the context of classification, the launch of the ImageNet large-scale visual recognition challenge in 2010 was one of the key moments driving this rapid progress. And in 2012, AlexNet's success raised expectations for AI, and by 2015, ResNet set a new benchmark by surpassing human-level performance in image recognition on the ImageNet dataset. In 2017, the transformer model was introduced in the context of natural language processing, and by 2020, it was applied to image recognition with the vision transformer, or VIT, and pushing the boundaries even further. I will not explain why transformers are here, and as I know most of you are already familiar with them. And for the purpose of this presentation, it's enough to understand them as a powerful component widely used in modern AI, including like ChatGPT. And here we see the top 1 accuracy on ImageNet of each model over the years. As of 2024, OmniVec, which is based on the Vision Transformer, represents the top performance in image classification tasks on ImageNet dataset. And while the search for better architecture and continues and new models are being developed, it seems that the pace of innovation in the core component of AI, such as residual blocks and attention mechanisms, has somewhat stabilized. Of course, this doesn't mean that progress has halted, but rather that the field has reached a point where these essential building blocks are now somewhat established. A similar trend can be seen in segmentation and detection tasks. And now that image recognition technology has reached a certain level of maturity for some tasks, and let's take a brief look at how well it is performing in medical imaging, and here in chest CT scans. And according to a review article in the JJR in 2023, AI has an 86.2% detection rate of primary nodules on chest CT scans, and this is in 2019 compared to radiologist. It surpassed the radiologist performance, and though it also produced more false positives. For more complex tasks, AI predicted 2 years overall survival, and in lung cancer characterization, AI models could predict genetic mutation like EGFR with AUCs ranging from 0.748 to 0.8, and especially when combining imaging with clinical data. As these examples shows, by around 2020, it becomes recognized that AI could handle a wide range of medical imaging tasks, from routine work to more advanced application at a practical level. The advancement of AI has not only led to research focusing on AI outputs, but also enabling the use of AI as a powerful tool in research. AI can automate time-consuming manual image analysis tasks, freeing researchers to focus on more complex issues. And moreover, AI has expanded the scale and scope of data analysis, enabling more comprehensive and impactful studies. And primary example of using AI as a useful tool in medical research is quantitative evaluation through segmentation. And segmentation, as shown in the illustration, is the technique that detects specific regions of interest at the pixel level. And by applying this to CT scans, it not only allows for the extraction of regions, but also enables the measurement of volumes and CT values. Previously, the focus was on whether AI could effectively perform organ segmentation. However, with the introduction of architecture like UNet, it becomes clear that AI could achieve the performance necessary for these quantitative evaluation tasks, making it a common tool in the field. And using AI for segmentation, we conducted a large-scale volumetric study involving over 3,000 participants who are GFR stage G2, meaning they had mildly decreased kidney function. And this is one of the largest studies of kidney volumetry. The histograms show the distribution of total kidney volume among male and female patients, respectively. These patients were followed up to 5 years to examine the prognosis of renal function. And during the follow-up, those with volumetry below 1 SD at The baseline were defined as the low kidney volume group. And this study demonstrated that even after adjusting for other risk factors for renal function decline, such as hypertension, diabetes, and smoking, the patient with low kidney volume had worse renal function prognosis. And this is one example of how AI can be used to process large-scale imaging data, and integrate it with other clinical information to uncover new insights. Through the efficiency and scalability of AI-powered analysis, we've been able to discover new knowledge from existing data. The one practical benefit of recent AI advancement is the ability to quickly build segmentation models for different organs by simply changing the dataset, often using nearly the same code, Python code. And this flexibility allows us to easily adapt and apply AI to various medical imaging tasks with minimal adjustment. For example, we were able to use nearly the same code to study thyroid CT density and analyze its volume. It's also really handy that the tools we need are so easy to get. We can find the Python code for these tasks on platforms like GitHub and libraries like PyTorch, TorchVision, and Monai. And it makes it easy to set up and use them AI models. These have made developing and using AI in medical imaging much faster. And up to this point, we've shown that with AI technology maturing for many medical tasks, some tasks can be automated, and AI can even demonstrate expert-level performance in medical image recognition. But does this mean that radiologists are no longer needed? Of course not. And let's consider the concept of a diagnostic radiology space, this space. And in this space, axes such as disease, modality, and body part can be set as example. And conceptually, the work of a radiologist covers all areas within this space. And now let's try plotting some AI application in this space. Okay. And for example, in this space, we might put AI solutions for detecting lung nodules in CT scans. This is a well-established application where AI has shown strong performance. And similarly, there is an AI solution for detecting brain aneurysms in MRI scans. This is another specific application where AI is being effectively utilized. And however, even if we brought all the currently available AI solutions in Japan, I think everyone can see that this space is still quite sparse. And moreover, the existing AI solutions are not evenly distributed across this space. Instead, they tend to be concentrated in specific areas. This clustering often occurs because certain datasets are more easily available or because development has focused on more commercially valuable applications. And additionally, there are many other dimensions not reflected in this diagram, such as age and country, and making the actual radiology space even more vast and complex than what I have represented here. And we need to plot more and more solutions or larger solutions that fill this space comprehensively. And to achieve this, foundation models and large language models will play a crucial role. And foundation models, which are large-scale AI systems pre-trained on vast amount of data, provide a strong base for various applications in radiology. They will help establish high-performance AI more quickly than before. And large language models are advanced AI systems capable of understanding and generating human-like text. Recently, multimodal models that process both text and image have emerged, offering even greater potential for radiology applications. And while fine-tuning these models for specific radiology tasks is not easy, doing so could significantly expand AI's capabilities and enhance its utility across the radiology space. And I think these are the best tools currently available to researchers for placing new points or expanding existing ones in the radiology space. Okay, to further drive the development of solutions using FMs and LLMs, I would like to introduce some studies that evaluate the performance of these models. For FMs, I will focus on segmentation tasks. Recently, the Segment Anything model version 2 was released, and SUM is a versatile AI model designed for general-purpose segmentation across various types of images. And although this model is not specifically designed for medical imaging, by treating a series of CT images as a video image, this model can perform zero-shot organ segmentation. And this slide shows a result of multi-organ segmentation of our method, with dice coefficient indicated in the parentheses. The dice coefficient are ranging from 0 to 1, where 1 indicates a perfect match, and generally a score above 0.8 is considered good performance. And while these examples represent some of the best results we achieved, it's still remarkable that a model not especially trained on medical images could achieve such high dice coefficient in a zero-shot setting. And we are currently evaluating how well these foundation models for segmentation, such as Total Segmentator, SPRIM, and some families, and perform in the organ segmentation using real clinical images from Japan and using JMIT. And although we can't share the full result yet, these models appear reasonably robust, and they certainly help minimize the effort required for the segmentation step. With this level of performance, I believe researchers can more quickly move on to downstream or more complex tasks, such as building AI for lesion detection and disease classification. And I'd like to shift to the topic of LLMs. And since the release of ChatGPT, LLMs quickly became a popular topic, and their influence has extended into the medical field. Amid differing opinion on the medical knowledge capabilities of these models, we explored potential use case, especially for radiology. To do this, we conducted an evaluation where we tasked GPT models with diagnosing diseases based on radiological findings from AJNR quiz cases. The AJNR quiz cases are challenging diagnostic quizzes presented in the American Journal of Neuroradiology. These cases often involved complex imaging findings requiring a deep understanding of neuroradiology to arrive at the correct diagnosis. And in this evaluation, we primarily had the GPT model interpret the radiological findings in the quiz and suggest potential diagnosis. And additionally, we assessed the model's capability to generate appropriate search queries for PubMed to help narrow down potential diagnosis based on the imaging findings. Through these approaches, we aim to assess how well these models could be adapted to radiological tasks. And here are the result figures, and the specific numbers are not particularly important. Even with the same object and model, different approaches led to variation in final performance. Additionally, combining approaches could result in improved outcomes like that. And we also observed an important improvement in accuracy when moving from GPT 3.5 to GPT 4, suggesting an accumulation of medical knowledge in the newer model. The models achieved a correct diagnosis rate of around 30 to 40%, while this indicated that the models possess some level of medical knowledge. It would not be comparable to expert level performance, not a direct comparison though. And recently, multimodal large language models like GPT-4V have expanded beyond the text processing to include image recognition capabilities. And to evaluate how effectively GPT-4V can handle medical images, we tested its performance on the Japanese National Medical License Examination, and focusing on questions that included both text and images. In this study, GPT-4V was presented with 108 questions that have accompanied images. We tested the model under two conditions, one where it had access to both the text and images, and another where it only had the text. And interestingly, the result shows that GPT-4V's accuracy was 68% with images and 72% without. Here and here. Indicating that the inclusion of images did not significantly improve their performance. This suggests that while GPT-4V can process images, its ability to use this visual information effectively in a medical context is still limited. Okay. In a more imaging specific scenarios, we evaluated GPT-4 with Vision GPT-4TV against the text-only GPT-4T in the context of the Japan Diagnostic Radiology Board examination. For this evaluation, we used questions from the 2021 and 2023 exams carefully selected by 6 board-certified diagnostic radiologists and who provided ground truth answers. And we focused on assessing the model's ability to process both text and image input, like national exams. And GPT-4TV, which had access to both text and images, achieved a correct answer rate of 45%, while GPT-4T, which is only used text, scores slightly lower at 41%. A statistical analysis showed no significant difference between the two models, and moreover, the score assigned by radiologists were actually lower for GPT-4T3, indicating that adding image input did not necessarily improve the model's performance in the specific medical context. Now, some might see these efforts as merely engaging with the latest trends for the sake of novelty, but there is a more significant purpose behind them, and we aim to thoroughly evaluate where these cutting-edge technologies fit within the diagnostic imaging space, and what form they take, all in the pursuit of expanding our knowledge. And furthermore, we are actually exploring how to advance these technologies and are committed to implement those developments now. And I hope to be able to show you significant results within the next few years. Okay, so let's return to the current state we discussed at the beginning. AI models are often capable of achieving sufficient performance in individual solutions. However, there is still lack of diversity and quantity in these solutions. And with the advent of foundation models and LLMs, we now have the groundwork in place to accelerate development from here. Okay, so where do we go from here and what's next? Let's move on to the next session. Based on the current relationship between radiology and AI, I believe the future direction of revolution can be broadly categorized into 3 main areas. First, there is the technological advancement of AI itself. This includes the continuous development of more sophisticated and powerful AI models in this field. And second, we need to focus on expanding the coverage of AI solutions in the radiology space and expanding AI solutions across different modality and diseases and body parts is crucial. And finally, the third direction is optimizing AI utilization by integrating AI more deeply into radiology workflows, so we can raise the overall level of diagnostic accuracy and efficiency. And these three areas are not independent, but rather influence and reinforce each other. And ultimately, there is a unified goal to benefit both patient and healthcare providers. And today we are going to focus on optimizing AI utilization. So optimizing AI utilization in radiology depends heavily on how well end users, particularly radiologists, adapt and integrate AI solutions into their workflows. And there are a few key considerations to keep in mind for achieving this optimization. First, it is essential to thoroughly address the practical aspects of AI use in real-world clinical environments. This involves discussing how AI can be utilized practically in day-to-day clinical setting. And second, AI must be accessible and usable by all radiologists, not just those with specific resources or expertise in AI. And third, improving AI result presentation and viewer usability is vital. The way AI results are presented, along with the availability of user-friendly AI viewers, is critical to their adoption and effective use. And finally, it can be said that AI, along with its effects and the surrounding environment, is transitioning to a large-scale social and clinical validation phase. And here I'd like to introduce the Abierto Leading Support System, RSS, as a practical example of how AI can be integrated into radiology. As the number of AI solutions continues to grow, traditional PACS viewers alone may not be able to handle the increasing demand. A study highlighted that dedicated AI viewers could improve diagnostic performance. The Abierto RSS is designed to address this issue, providing a more advanced and user-friendly platform for AI-assisted image analysis or computer-aided detection. The following 7 slides are provided by Canon Medical Systems Corporation. The Abierto RSS is a system that sits between the modality, such as CT or MRI, and the PACS, which is the image storage and retrieval system, and also contains the viewers. And it contains RSS contains two main functions: the automation platform, which is the analysis server, and the finding workflow, which is the dedicated viewer. And when images are received from the modality, and the automation platform automatically performs the analysis for each AI. Each AI applications, and give to the finding workflow the result, and we can see a result in this viewer. The automation platform provides a core analysis function upon receiving images and the type of launching that corresponding analysis application. This platform supports application from both Canon Medical Systems and other third parties. Additionally, it supplies analysis information to the finding workflow, allowing the result to be viewed in the optimal layout. And let's consider the traditional use of AI with a traditional viewer. When viewing AI analysis result in a standard reading viewer, it is often done using DICOM secondary capture images, or SC. And DICOM SC in this context refer to images where AI-generated results such as overlays or annotations have been added to the original DICOM images. And this method can be burdensome as it requires aligning the SC images with the original images, which increases the workload by having to check the alignment. And one of the key features of the Abierto RSS is its support for comprehensive finding workflow. This includes preparation for reading, such as image alignment and sorting, as well as checking previous reports. The system also facilitates the preparation of reports by verifying images and pasting key images into the report, Additionally, it supports the review of AI analysis result, including recording, reordering images and adjusting layout before confirming and revising the report. And the user can also modify analysis result and easily paste them into report. Freezed. Okay. And here is the actual viewer screen of this system. The analysis results are clearly displayed and allowing you to understand the full result at a glance. And compared to SE-based result display, this workflow offers greater flexibility, enabling not only viewing but also modification to the result. Additionally, the image layout and resolution presentation basically consist across different applications, providing a unified user interface. And the Abierto RSS offers 3 core values, which are as followed. First, operation value. The platform ensures smooth and efficient image analysis process, reducing the workload on radiologists. And the second, clinical values. It supports various applications, enhancing the clinical utility of AI in radiology. Third, a subscription-based model. The solution is offered through a subscription-based contract and providing continuous update and access to the latest advancement in AI solutions. These 3 values make the Abierto RSS a comprehensive and forward-thinking tool for integrating AI into radiology practicals. And these are the currently available applications on the Abierto RSS, including a tool for temporal subtraction in bone analysis, lung nodule detection and measurement in chest CT, and ischemia analysis in the brain, and detection of brain aneurysms in MRI scans. While the variety of application is not yet comprehensive for daily radiology practice, the development of these advanced applications demonstrate the potential of AI to become an excellent tool in modern radiology with Abierto RSS. And then I would like to share my own initial experience using Abierto RSS. And first, radiologists typically work with 2 or more displays side by side. On the left, we often have the reporting windows where the radiologists write up image findings. On the right, we have the screen displayed the diagonal images. For example, when using a CAD system to detecting lung nodule on a chest X-ray, and then reviewing finding with the corresponding CT images, the layout might look something like that. And let's consider a scenario where aneurysms are detected in MRI TOF images. And these images represent a typical case where aneurysms have been identified and the region areas have been annotated in the diagram SC format. And we need to verify whether this is truly an aneurysm. With traditional viewers, this process involving placing the diagram SC images and next to the MRI TOF images, then scrolling through the TOF sequence to check to detected areas, which aid extra steps to our workflow. And there are also some additional issues to consider, such as the fact that SC often displays results in actual views only, and there is no correction function for errors, and meaning inaccuracies may remain in the system without being corrected. In the Abierto RSS, the AI analysis result can be displayed on a platform that supports 3D visualization, and there is a maximum MIP images where all detected results can be overviewed, and each region can be observed in actual coronal and sagittal views. And additionally, there is a sidebar on the left with thumbnails that allows you to quickly jump to the detected regions. And there is also a button to removing false detectives. And moreover, paste to report button is included, and which is useful for writing reports. And additionally, by double-clicking on any view, the image is expanded, allowing users to seamlessly evaluate whether the detected region is indeed an aneurysm using the sequential images, like that. Okay. So another example is that radiologists is often needed to track and compare various regions. A simple case is the follow-up of lung nodules. This involves placing the current and previous images side by side, confirming the region at the same location, measuring its maximum diameters, and then describe any changes. To achieve such a displayed layout, the radiologist must repeat some simple routine steps many times a day. In RSS, there is an automatic region tracking function using registration techniques and an automatic size measurement function through segmentation. When you first open the analysis results screen for a case, it can be displayed in this kind of layout. In this case, it seems the diameter has increased from 9.37 millimeters to the 30 millimeters. With this example, some might think that doing this measurement manually for a single region wouldn't be too much of a task. However, in cases with multiple lung metastases, where evaluating numerous regions after not changing in treatment or checking for new region is crucial, this application may reduce radiologist workload. And this type of comprehensive reading isn't limited to the lung nodules, and ideally it should be applied to the entire range of images. And as you know, conducting a comprehensive comparison of the entire body is an incredibly labor-intensive task. So particularly when new regions emerge, they may initially be presented with only subtle changes. Detecting bone regions is one of the crucial tasks for radiologists in cancer care, but it's not always easy to identify in every case. In this case, the patient undergoing cancer treatment developing metastasis in the ileum and sacrums. And can you find them? Okay, when comparing with images taken later, the areas of changes become slightly more apparent. But identifying these changes across the entire body during a comprehensive evaluation would be a highly challenging task. By utilizing the AI application with the bone subtraction features on MRI RSS, the areas where CT bars have changed between the two images are highlighted in the different colors. Of course, whether to consider these results are metastasis is up to the radiologist's judgment. While this might add some steps to the reading process, I believe it can help detect areas for focused evaluation, potentially enhancing sensitivity. And this is an example of how this application appears on the actual viewer and with different cases. On the far right views, the potential region areas are highlighted in color overlaid on the 3D reconstruction of the bone image, making it easier to identify key areas for focused evaluation. And additionally, though this is a slightly different context, supporting emergency diagnosis is also crucial for reducing the workload of clinicians. And clinicians often have to make critical decisions within minutes. And here is a head CT scan. And can you find any findings? So if you are experienced, you might notice the hyperdense MCA sign and recognize the loss of gray-white matter differentiation, identifying an infarction in the right MCA territory. And sometimes these critical decisions have to be made immediately after waking up. And on the right, you can see the analysis result of ischemia analysis application on RSS, and with the suspected infarct areas in the right MCA territory highlighted on the heat map. In fact, an MRI taken immediately afterward shows an infarction in the same areas. Okay, so having used RSS, I'd like to share my initial impression. The design of RSS is not merely an additional burden on traditional reading process. Rather, it is designed to maximize the benefit of AI with minimal additional cost, or to reduce the effort involved in interpreting without compromising quality. I believe RSS will be a key platform as we enter an era of large-scale social and clinical validation of AI. Additionally, with the growing integration of generative models, including LLMs, into clinical practice, and I expected RSS to evolve further to meet the demand of these new AI-driven solutions. And we are currently setting up an independent practice environment centered around we are currently setting up an independent practice environment centered around Abierto in our laboratory to accelerate AI research. And this is because research in an environment close to clinical practice is essential for the rapid development, validation, and incorporation of such new solutions into healthcare. And as we near the end of this presentation, I would like to share 2 examples briefly that shows radiology itself continues to advance. I mention this because radiology is sometimes seen as a field that have already reached its peak and stopped evolving by someone. And first, even in recent years, new image findings have been discovered and named to help differentiate diseases. A relatively recent example is the identification and naming of the milfoil sign in ovarian tumor in 2020. The milfoil sign on MRI describes a tumor that looks like it has layers similar to the layer in a milfoil pastry and due to different tissue densities. This finding has been reported to be useful in differentiating ovarian metastasis from primary ovarian carcinomas. And additionally, in 2024, this sign was also found to be characteristics of ovarian carcinosarcomas. And this highlights that there are still many undiscovered facts in the field of radiology, even in images from existing modalities. So even in retrospective image reviews, such new findings can still be discovered. As part of the ongoing advancement in radiology, imaging modalities are also evolving. Recently, the development of photon counting CT, PCCT, has become a major topic of discussion. So I'm sorry that I can't go into technical details here, but in short, innovation in X-ray detectors have enabled CT images with much greater potential, offering significant improvements like higher spatial resolution, reduced radiation dose, and advanced material differentiation. And you can find several examples on Canon Medical Systems website, which should give you a good sense of the potential of PCCT. And I'll share just one example here. On the right is a high-resolution image taken with PCCT from a patient with oral cancer, and on the left is a standard resolution image for comparison. And you can see much more details in the tumor structures with high spatial resolution image. And this could also potentially lead to the discovery of new findings and enable more precise diagnosis. Okay, we are entering the conclusion of this long presentation. I have shared my perspective as a radiologist on the current state and future direction of AI in radiology. And I discussed the clinical performance and the limitation of current solutions and the growth potential brought by foundation models and LLMs. And when considering the direction of evolution, I highlighted 3 key areas. That is technological advancement, expanding AI solutions, and optimizing AI utilization. And today I introduced the Abierto RSS as a solution for current and future AI utilization. And finally, I emphasized that radiology itself continues to advance. To bring high-quality AI solutions to clinical practice, it is essential to continuously update both radiology and AI knowledge in parallel, which requires expert collaboration. And I look forward to seeing high-quality AI solutions developed through the collaboration of various experts and integrated into this platform as diagnostic tool. And of course, I also feel a responsibility to contribute to this development myself. Okay, this is acknowledgement, and I appreciate your time and interest in this presentation. Thank you.